So now we have obtained Penrose Carter diagram for the black hole. Let me draw it more carefully now. And I'm going to use it to show some qualitative properties of the black hole space-time and show you why it is a convenient tool to study physics and geometry of space-time. So the diagram that we have obtained is as follows. Let me draw it more carefully. So this is a light-like line, light-like line. So this is, I didn't draw it carefully on the previous board. So let me draw it more carefully. So this is parallel to this. This is parallel to this. And this is a straight angle, 90-degree angle. This corresponds to r equals to 0. This corresponds to r equals to 0. This corresponds to r equals to rg. This corresponds to r equal to rg. This part is covered by Schwarzschild coordinates, only this part. And now, as usual, light rays in this space, can be represented by straight lines going like this. Light rays are like this. So this is scry minus. This is scry plus. This is scry minus. This is scry plus. And this is actually I0. This is I minus. This is past infinity, future infinity. Past infinity, future infinity. As time goes by, as this big T time goes by, this light rays are directed like this. These lines are also light rays, light-like. As you remember, this corresponds to V equals to 0 and U equals to 0, which is light ray, of course. And what is important that this space, now let us describe properties of this space. Now one can see immediately the difference of this space, of this Penrose diagram with respect to the flat space diagram. In the flat space diagram, every observer had an access to all Cauchy surfaces as it approached future infinity. Here, the situation is quite different. We have a funny thing that if someone, for example, appeared at a point here, for some reason appeared at a point here, light cone, future light cone, starting from this point, goes like this, and one will inevitably end up at r equals to 0, because any massive particle or observer has a world line going within the future directed light cone. So inevitably it will end up in the singularity. So if you found yourself inside a Schwarzschild black hole, you inevitably end up, to avoid ending up 0, r equals to 0, is the same as to avoid next Monday. Moreover, light ray emitted from here never gets here. So for example, if an observer which is fixed above the surface of the black hole goes along hyperbola, which corresponds to r constant. That hyperbola in Kruskal-Zekeres space-time is mapped to something like this here. So this is, if you are fixed above the black hole, you go along this world line. Or for example, if you circle around the black hole because you forget about the angular part of the space-time, circulating around the black hole is not sensitive. This diagram is not sensitive to the circulation around the black hole. So if you orbit around the black hole at a fixed radius, your world line will look more or less the same. So an observer from here never see a signal from anyone which is here, from anyone which is living here. So this region is called black hole. Here the situation is quite opposite. If one appeared here, he will inevitably run out from this part. Inevitably run out. And this place is called white hole. White hole. So, but we have some kind of doubling. So we have a black hole, and on top of that, so we have an exterior region to the black hole. We have interior region of the black hole, and we have also interior region of a white hole and exterior region to the white hole. And we have some kind of a doubling, and it is actually easy to expect if one recalls that general theory of relativity is time reversal invariant. Well, let me explain it in a bit different manner. So there is a way to represent general theory of relativity in the Hamiltonian form, which goes beyond our lectures. And this Hamiltonian form is invariant under the time reversal. So then it means that for every solution of general theory of relativity, there is a solution which is time reversal of that solution. So if one considers a space-time which is static, so which is invariant under this transformation and time translation, it is inevitable that complete covering of that space-time will contain both parts, the original space-time and its time reversal. So that's basically the vague explanation why we have simultaneously for the static Schwarzschild. In the next lectures, we will see that for the different situation, there will be present only some part of this space-time, and for what reason we will explain. So, but this fact that I described to you can be observed also with the picture that we have encountered in the previous lecture. At the very end of the previous lecture, we used ingoing Eddington-Finkelstein coordinates, and in those ingoing Eddington-Finkelstein coordinates, we had this is r equals to 0 singularity, and so we had the following situation. We had the horizon, which is one of the, this is r equals to rg, so it's similar to this situation. So r equals to rg, which is one of the light rays, similar to these guys. These are light rays, also light-like surfaces. And now ingoing light rays, if you remember, were like this. Ingoing light rays were like this in the picture that we have drawn at the very end of the previous lecture. And outgoing light rays had this behavior. So you see this kind of situation that I have described here can be seen also in this picture. For example, if somebody found himself here, somewhere, say here, its future-directed light cone is like this, so you inevitably go to the singularity. So this is a black hole region. So light rays cannot escape from here. You see, there is no light like geodesic which goes from this part to outside. So this is a similar situation to this. During the next lecture, we will describe quantitatively these effects that we are now going to explain to you qualitatively on the Penrose diagram. So let me draw it again. So the Penrose diagram, let me draw it here. So the Penrose diagram is like this. So again, so these are light-like, and this is light-like, Scri plus, Scri minus. And now suppose there is an observer which is fixed above the black hole. Its world line, as I just explained, is like this. Or any observer which stays always outside the black hole has a world line something like this. So let me call this observer as number 3. So which always, throughout all its life history, stays outside of the black hole. And now suppose this guy drops off at some point something going inside. Object number 1. Now one can see immediately, well, we're going to show explicitly in the next lecture that it takes a finite proper time for this thing to cross the horizon. Finite proper time. It is a finite, this line is for finite lengths. And the length of this guy is proper time spent from here to here. It's a finite length. But at the same time, one can see that light ray, so this observer, which stays always outside of the black hole, will never see this object number 1 crossing the horizon. Indeed, the last light ray, which is emitted by this guy at the crossing of the horizon, will reach this observer number 3 only at the future infinity. So that never happens. Never happens. Although this guy takes a finite proper time to cross the horizon, and even actually to reach the singularity. So indeed, this is very similar to what we have encountered in the first lecture in the description of the Rindler spacetime. Remember that this surface is future event horizon. This is actually past event horizon of the Schwarzschild, so this is future event horizon. It corresponds to u equals to 0. At the same time, it corresponds to r equals rg, but also it corresponds to t equals plus infinity. And remember, this t is the time as measured by observers which are fixed above the Schwarzschild black hole. Non-inertial observers which are fixed. But also it takes infinite time for the observers which are not necessarily fixed, as I have shown to you here. So in fact, it's similarly to what we have encountered in Rindler space. You remember that rho equals to 0 was the Rindler horizon, and it as it was, so it's t tau, the Rindler time. So finite amounts of proper time in the Rindler space-time as rho approached to infinity, to 0, was corresponding to bigger, longer and longer amounts of the coordinate time, Rindler time tau. Here we encounter the same situation. ds is equal to 1 minus rg divided by r 1/2 dt. So this is a relation between proper time and coordinate time in Schwarzschild space-time. And as r approaches the rg, finite proper times correspond to bigger and bigger amounts of the coordinate time. This is another way to see this thing. Well, the same statement that I have said. But what is interesting, on the other hand, that if someone was falling after this body number 1, someone was falling, accompanying it just a little bit later. Observer number 2 was going right after this guy to the black hole. This guy would never lose this body from his side because he would receive always light rays coming from this guy. But what is interesting that it will see this body when the observer number 2 stays outside of the horizon. It sees this body also outside of the horizon. But when it crosses the horizon, then it will start receiving the light rays refracted or emitted by the body number 1 after the crossing of the horizon. So, but it never loses this thing from his side. So we can qualitatively see properties of the black holes with the use of the Penrose Carter diagram. So you see there are causally disconnected regions, so one never can emit something from here that can be received here. So this is the reason this guy is called black hole. And so this is the advantages of the Penrose-Carter diagrams. The disadvantage is that to draw it, one has to know the space-time, entire space-time, which is frequently in the real physical situation happens to be not always possible. But otherwise, if it is possible, then you can draw select relevant two-dimensional part and draw the Penrose-Carter diagram and understand causal properties of the space-time. That we will do actually in the next lectures for different sorts of space-times.